I don't know if aliens exist, and I can't prove it either way. But what we are going to do is proof by induction. And what we're going to prove is that the sum of the first n positive integers is equal to n times n plus 1 divided by 2. So I've actually written it here. S sub n represents the sum of the first n integers. And in detail, that would be 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way up to n. And that's equal to n times n plus 1 over 2. We're going to prove that by induction, but first I'm going to prove it another way, and I think this way will be accessible to more people. The story I was told is that Gauss did this when he was 5 years old. So that's quite impressive, I think, for a 5-year-old. But what I'm going to do is I'm going to write this again. So S sub n equals 1 plus 2 plus 3 plus dot 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 plus n. And then I'm going to write it again, but I'm going to write the right-hand side backwards. So S sub n equals n plus the integer before n is n minus 1 plus the integer before n minus 1 is n minus 2, and then plus dot 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 all the way down to 1. And then I'm going to add these two equations together. I think it's important to understand that S sub n and n are not variables in these equations. N is an unknown constant. It's a positive integer. We're going to set that. And S is the sum. But there's no variable here. So when I add these two equations together, I think we've all done this before in systems of linear equations where we use the elimination method and we add equations together in such a way that we eliminate one of the variables. So you can always add equations together. There's no issue with doing that. Whenever you want, you can always add equations together. The key is recognizing when it's useful to do that. And in this case, it's very useful. And I'm going to say again, Gauss did this when he was 5, which is just amazing to me. But, okay, now we're going to add these equations. S sub n plus S sub n is 2 S sub n. And that's equal to n plus 1 is n plus 1. And then n minus 1 plus 2 is n plus 1. N minus 2 plus 3 is also n plus 1. Plus dot 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 plus, and the last one is n plus 1 as well. So 2s sub n is equal to n plus 1 plus n plus 1 plus n plus 1 plus n plus 1 all the way down. So how many n plus 1s are there? Well, there's one n plus 1 for every term in the original expression and every term in the second expression. I think the number of terms is easier to see here. How many terms are there? Well, there's n terms. So that means that 2 s sub n equals n times n plus 1. Now we're going to solve for s sub n. Now S sub n is starting to look like a variable because we're going to solve for it. So I think I'm splitting hairs now, and you could argue that either way, but I have an example where I think it'll be more clear that this actually isn't a variable, even though we're solving for it. We're solving for S sub n is the sum of the first n integers, and right now we're just going to divide both sides by 2, and we get S sub n equals n times n plus 1 divided by 2. So the sum of the first n integers is n times n plus 1 divided by 2. You can try that with, a few numbers. Try it with n equals 5. So the sum of the first 5 integers which we would write as s sub 5, well, that's equal to 1, 1 plus 2 plus 3 plus 4 plus 5. And I'm going to add these from right to left, so 5, 9, 12, 14, 15. So that's equal to 15. And then s sub 5, just using the formula that we have here, would be 5 times 6 divided by 2. And that's also equal to 15. Yes, 15. So that confirms it for a number, and you can do it, you can try it again and again, and you can confirm that all you want. I hope that this is clear, because we really don't need to confirm it, because the proof we just did, completely confirms it. I mean, the sum of the first n integers is n times n plus 1 divided by 2. But it never hurts to do it with a few numbers, but it's going to be pretty hard to do it with a number like a million, because you're not going to add 1 plus 2 plus 3 all the way up to a million. But using this formula, it's just a million times a million and 1 divided by 2. And that would be the sum of the first million integers. And then now we're going to do that same proof by induction. But before I do that, I want to make it clear that these really aren't, s sub n and n really aren't variables. They're unknown constants. So s sub n is the sum of the first n integers. That's what it represents. And n is the nth integer in the series of the first n positive integers. But that's an unknown, that's a constant that we set. This is the sum of all that. And I think the fact that those aren't variables will be more clear here in this example, which is just, this is like a side note, just to add clarity to me claiming that those aren't variables. So if I said x equals 0.45 repeating, this is a repeating non-terminating decimal. So that means that it is a rational number, and it is not an irrational number. Remember, an irrational number is a non-repeating, non-terminating decimal. So this is a rational number, and we know that rational numbers can be written in the form of a fraction. So our job now is to rewrite this in the form of a fraction. But I think it's clear that x isn't a variable, right? X is equal to that number. So there's no variable here. I mean, x is equal to that number. X can't change. X is a constant in this particular case. But what we're going to do to accomplish what we want is I'm going to multiply x by 100, and I'm going to write that right above. So we have 100x. Well, we know multiplying by 100 is just moving to the decimal places, 2 places to the right. So 100x is going to be equal to 45.45 with the 4-5 repeating. Now we're going, remember, I have to reiterate, x is not a variable. So we just want to write x in a different form in this particular case. So I'm going to subtract the second equation from the first equation. And 100x minus x is 99x. And 45.45 repeating minus 0.45 repeating is just 45. And now we're going to isolate x on one side of the equal sign. We're going to kind of, we are treating it as if it's a variable from all of our experience in solving equations. But x never was a variable in this whole thing. We're just re-expressing x in a different way. So I'm going to divide both sides by 99, and you get x equals 45 divided by 99. So I think this is a good example of where x isn't a variable, but nevertheless we work with what we've got to accomplish our goal. And our goal was to rewrite this number as a fraction, because this number is a rational number. It's not an irrational number. Remember, irrational numbers are non-repeating, non-terminating decimals, like pi or e, or you can just make one up, point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You know, when I say 10, I mean 1, 0, 11's 1, 1. That would be a non-repeating, non-terminating decimal, and that's an irrational number. So, okay, that all said, now we're going to prove the same thing, but we're going to do it by induction. When you do proof by induction, the first step is to assert what you're going to prove. This is your premise or your hypothesis. So what we're going to prove is S sub n equals n times n plus 1 divided by 2. So this is step 1. Then step 2 is to show it's true for some n. So step 2 is going to be, let's just choose n equal to 3. So S sub 3 equals, using the formula, 3 times 4 divided by 2. That's equal to 12 divided by 2, which is 6. And we can see that agrees with, if we were to do it manually, the sum of the first 3 integers. S sub 3 is the sum of the first 3 integers. 1 plus 2 plus 3 is 6. Then the third and last part is the actual inductive process. So this is a little bit difficult to explain, I think. What we want to do is we're going to start with S sub n is equal to this, and we know it's true for at least one n. Then we're going to write S sub n plus 1 in 2 different ways. So S sub n plus 1, well, that's equal to S sub n plus n plus 1. All right, S sub n is the sum of the first n integers, and if you add n plus 1 to the sum of the first n integers, that is the sum of the first n plus 1 integers. Then we also want to write it just using the formula. So just using the formula, the sum of the first n plus 1 integers would be, we're going to replace every n with n plus 1. So we would have n plus 1 times n plus 2 divided by 2. And if you think about it, you can, this is the general case. We want to show this in the general case, which is why we're using n's and everything. But if we let n be equal to 3, we can kind of see that this statement is reflective of what we're trying to prove. So let n be equal to 3. If n is equal to 3, S sub n is the sum of the first 3 integers, 1 plus 2 plus 3. And then we're going to add n plus 1. That n plus 1 is 4. So this would be the sum of the first 4 integers. And if this n is 3, then S sub 4 is the sum of the first 4 integers. And we're, in just using the formula, S sub 4 would be 4 times 5 divided by 2. So if n is equal to 3, you have 4 times 5 divided by 2. Might take a couple seconds to look at that and realize what I'm saying is true, but it's worthwhile to spend a little time looking at it and understanding what I'm saying. So if we can prove that this is equal to that, then we're done. But let's just concentrate on these two expressions and show that they're equal. Well, we know that S sub n is n times n plus 1 over 2. So I'm just going to rewrite this as S sub n is n times n plus 1 over 2, and then plus n plus 1. And that's equal to n plus 1 times n plus 2 over 2. N plus 1 times n plus 2 over 2. And I've run out of board, so I'm going to clean it up a little bit. I ran out of space, so I just shifted this up so that I would have more space to do writing. But we're still trying to prove that the left side is equal to the right side. And when you demonstrate something like this, you don't want to work both sides of the equation. You don't want to move things from the left into the right and stuff like that. You only want to work on one side. So I'm going to choose to work on the left side in this case. And what I'm going to do is I'm going to multiply through and get a common denominator all in one fell swoop. Because I think if you're with me up to here, I can skip those steps and you'll still understand. And I'll explain them as I go along. So n times n is n squared. And n times 1 is n. So we're going to add n. But we've got another n over here, so I'm going to combine like terms. We want a denominator of 2. So to write n with a denominator of 2, that's 2n over 2. So we have n times 1, which is n, plus 2n over 2. So n plus 2n is 3n. Plus, and then the right 1 with a denominator of 2 would be 2 over 2. So plus 2, and then the whole thing over 2. Then all we need to do now is factor the numerator. And the numerator factors into n plus 1 times n plus 2 over 2. And now the left-hand side and the right-hand side agree. So we're done. We've proven that the sum of the first n integers is n times n plus 1 divided by 2. And we did that by induction. You can see that if it's true for some number n, then it's true for n plus 1. So you can think it through in terms of if it's true for 3, then it's true for 4. But if it's true for 4, then it's true for 5. If it's true for 5, then it's true for 6. And by that process, you can see it's true for all positive numbers n. So when I first saw this, one thing that I came to mind was, well, if you choose an n that's like 5 to test it, if I had chosen 5 here, how do you know it's true for 4? And how do you know it's true for 3? I can see how if you choose 5, it's true for 6, 7, 8, 9, and all the ones beyond that, but how do you know that it's true for the ones prior to that? And I think that's a really good question that you would, when you first see this, you would, if you're thinking about it and you're pondering these ideas and concepts, you'd say, well, what about? And I think that's something that you can do for yourself. You can do that on your own. You can figure that out yourself. You just would, instead of adding n plus 1 here, you would subtract n. So you would be adding the first n minus 1 integers, positive integers. And on the right-hand side, you would have n minus 1 times n divided by 2. So I encourage you to do that, to kind of convince yourself, and it'll help you understand this inductive process as well. I hope that you understood both of those proofs, but I hope you understood at least one of those proofs, or I hope you're at least convinced that the sum of the first n integers is indeed equal to n times n plus 1 divided by 2. But, even if you understood, I think some of you could be thinking something along the lines of, okay, that's sort of neat, I guess, if I was a dork. The thing is that you really don't know where these concepts are going to manifest themselves. And they manifest in the strangest of places. So consider this. Consider you're a tournament director and you're going to have a round-robin tournament. Round robin means that every team in the tournament plays every other team in the tournament. And as a tournament director or coordinator or manager or whatever you want to call it, there are many different hats that need to be worn in that kind of a scenario. But you might be charged with, securing a location and securing equipment and all kinds of things. So one thing you would need to know is how many matches you're going to have, because you need to rent facilities for a certain amount of time and all kinds of things are dependent on how long that tournament's going to last. So how would you figure out how many matches there are in a round robin tournament? Suppose for simplicity, it would just have only 5 teams, but you might have 100 teams or 500 teams. So suppose you only have 5 teams. Well, round robin means each team plays every other team once. So there's 5 teams. Every team has to play 4 teams. So there's 20 matches in all, right? That seems perfectly logical, and it seems intuitive. I mean, it seems easy. Yep, 20 matches. But I'd say that's wrong. I say we're double counting, and I think I can show you why. And this is where we would have an application of this formula to figure out exactly how many matches we're going to have. So I'll erase the board. Consider we have 5 teams in this tournament, and every team has to play every other team. So I'm going to represent the teams by a dot. So it's like team 1, team 2, team 3, team 4, team 5. And every team has to play every other team. So team 1 is going to play team 2, and team 1 is going to play team 3, and team 1 is going to play team 4, and team 1 is going to play team 5. So team 1 has played 4 matches, or each line represents a match. So team 1 has played all 4 teams now. And all we have to do is make sure that all the other teams have played all 4 teams as well. So now we would go to team 2 and say, well, team 2 has already played team 1. So team 2 doesn't need to play team 1 again, but team 2 needs to play team 3, and team 2 needs to play team 4, and team 2 needs to play team 5. So that's 3 matches. Okay, and now teams 1 and 2 have played all 4 teams. So now team 3 has to play team 4, and team 3 has to play team 5. Now teams 1, 2, and 3 have played all 4 other teams, but team 4 and team 5 hasn't played. So team 4 plays team 5. So how many matches do we have in all? Well, we just count the lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our intuitive logic said, well, 5 teams, each team plays 4 matches. That's 20 matches in all. Done deal. That's, really simple. But I think we just demonstrated that only 10 matches are played. And it's true that there's 5 teams, and each team plays 4 matches, but there's only 10 matches in all. So that, if you haven't seen that before, that probably seems strange. And let's see how we would apply this. Well, we know that the first team plays 4 matches, then the second team has to play, the first team plays the first 4 matches are team 1 playing the other teams. Now team 1 and team 2 have already played a match, so they don't need to play a match again. Then team 2 plays 3 matches, so that now team 2 has played all the teams. So actually, let me write this down. There's 4 matches to start, and then team 2 has to play 3 more matches, and then team 3 has to play 2 more matches, and then team 4 has to play 1 more match. So we see that's the sum of the first 4 integers. So this is an application where this would count. And if you had 100 teams, or 101 teams to make it a little simpler, and you just said, oh, 101 teams, every team has to play 100 matches, so that's 10,100 matches in all. You would be exactly double counting, and you would rent facilities for a period of time, equipment for a period of time. You would do everything under that assumption, and that assumption is just wrong. That would be a huge mistake, and you might end that particular venue without a job at the end, because that's just, you're deploying resources inefficiently. It's just, I hope you can see the problem that might ensue if you don't know how to do this really simple thing. So that is an example of where you would actually apply this type of stuff. I actually have another example, but this example is going to be more in the realm of statistics. So imagine that you're like a farmer or something. You do something where you need fertilizer, you know, and you actually need to buy 1,000 tons of fertilizer. So, and there's like 5 different fertilizers on the market that you can choose from, and they range in different prices. And what you would like to know, again, if you don't know statistics, you're not going to be able to follow this. But if you know statistics, this will make sense. So what you're going to do is gotta buy 1,000 tons of fertilizer. There's 5 different choices. You know, obviously the cheapest fertilizer is going to be the cheapest choice. What if one of the 5 fertilizers costs $50 a ton, and the most expensive fertilizer costs $200 a ton? Well, if you're buying 1,000 tons, that's a $150,000 difference. So it's really important to know if there's if the difference is significant enough to warrant spending that extra money, because you're growing something for profit, right? So you want the proper yield, you want the most yield, or you want the ripest fruit, or you know, whatever you're doing, you've got some criteria for what you want. But what we've got is 5 fertilizers. We need 1,000 pounds, and we want to compare these fertilizers. So the null hypothesis in this case would be that all the fertilizers work the same. So, and if that's the case, then let's just buy the cheapest fertilizer. We're saving money if we do that. The alternative hypothesis would be at least one of the fertilizers works better than the rest, or works differently than the rest. I guess it would have to be works better than the rest. So how you would do that is, this is leaning towards analysis of variance, but I think in this particular case you could do it with a chi-square. And chi-square is something that is done in high schools these days, or the statistics class will do chi-square, but you don't really go into ANOVA or analysis of variance. So if you were to employ chi-square, you know, back up just a little bit. So you have choices. You can either, you know, compare each fertilizer to every other fertilizer, do a t-test to do that comparison, and you know that, you know, the probability of making a type 1 error, which would be rejecting the null hypothesis when the null hypothesis is true, is equal to the alpha level of significance. And the typical alpha level of significance is 0.05. So you have a 5% chance of making a type 1 error. But if you were to try to do this in a t-test, so you compared every combination of 2 fertilizers to each other, you would be doing 10 t-tests. By using this formula, it's 10 t-tests. If you were to think in your head, well, okay, there's 5 fertilizers and I'm going to compare each one of them to 4 fertilizers, then I'm going to do that. I'm going to do 20 comparisons then. So you would be overcounting that. And what chi-square does is it allows you to compare all the fertilizers to each other at once. So you'll be able to see if there's significant evidence that one of the fertilizers is behaving differently, hopefully better than the rest, you know, and then you can do more testing to see if it's warranted to spend the extra money to go with that fertilizer or not. But if you were to do the t-test, the probability of making a type 1 error, rejecting the null hypothesis when the null hypothesis is true, is 0.05. So the probability of not making a type 1 error is 0.95. And you would have 10, you would be doing 10 paired comparisons. So the probability of not making a type 1 error 10 times in a row is 0.95 to the 10th. And so the probability of making a type 1 error in in at least one of those 10 tests would be 1 minus 0.95 to the 10th. And 1 minus 0.95 to the 10th is approximately equal to 40%, or 0.40. You know, should have done this before I did it, but I need to verify with the calculator. 0.95 to the 10th equals Yeah, so this is right. This is approximately 0.4. So we have a 0.4 chance now, if we were to do the test that way, 10 t-tests to make this one test to see if there's a difference. The probability of us making a type 1 error in at least one of those 10 tests is 0.4. And that's if you know statistics, that's just too, it makes the whole study irrelevant now. I mean, 40% of the time you're going to make a type 1 error. So it's just dumb. And if you were to compute it as, there's 20 different ways, it would be 1 minus, again, this is incorrect, but this will magnify the error here. So it'd be 1 minus 0.95 to the 20. And that's approximately equal to, need the calculator again, sorry, I should have done this before, but I didn't. 0.95 to the 20 equals, be right around 64%. So 0.64. So the probability of making a type 1 error, which is rejecting the null hypothesis when the null hypothesis is true, is 0.64. And in reality, if we had done that calculation right, the probability of making a type 1 error is 0.4. And that's just not reasonable to even do the test. The test becomes meaningless because due to random variation, you're going to observe that one of the fertilizers is significantly better or worse than the other fertilizers 40% of the time. So it just makes the whole study irrelevant. So I hope that makes sense. And where this would come in is just in thinking through that process to understand what it means to try to do that type of a comparison with a t-test. You run into this problem. And think about it. You actually don't want to reject the null hypothesis. So doing these paired t-tests increases the likelihood you're going to reject the null hypothesis. If you can, for valid reasons, not reject the null hypothesis, then that means that you can just go ahead and go with the cheapest fertilizer, thereby saving your company maybe as much as $150,000 on buying fertilizer. So feel free to comment, feel free to make suggestions that will allow me to improve what I'm doing here, make corrections if you think something is wrong, all of the above. Anything you think would be relevant. Please hold the criticism to constructive criticism, but anything is fine, I guess. And once again, thanks for listening. Thanks for spending the time. Thanks for listening.